Right. So section 6 is gravity and orbits. So we're talking about space, which is great. A smaller object in orbit around another larger object is called a satellite. So a moon around a planet would be a satellite. A planet around a star would be a satellite.
Satellite around the Earth.
A satellite around the Earth would be a satellite. Okay. The International Space Station is a satellite. Those are all satellites. Anything orbiting something else that's larger than that thing is a satellite. So if we model an orbit as circular motion, then Newton's second law tells us that F equals ma, of course. So we have the mass of the bigger thing on the mass of the on the smaller thing equals ma, where Fm on m, big M on little m, is the gravitational force of the large body on the satellite, and a is the satellite's acceleration. So if we solve for v, then we have the speed of the satellite in circular motion, or in circular orbit, is v equals the square root of gm over r. So if we look at that equation, what do you notice about that formula as it relates to the satellite's speed?
It looks a lot like something else we've done.
It does look like something else that we've been working with, but in the formula, how does the speed change?
If its radius is increased, its speed is decreased.
Okay, if we increase the radius, okay, then so that makes the fraction smaller, which would create a smaller velocity. No, if we increase the radius, that makes the fraction smaller, which would make a smaller velocity.
Yeah.
Yeah. Okay. So what else?
If you increase the mass, then the mass is going to make a bigger velocity.
If we increase the mass of what?
The mass of the planet.
The mass of the planet, because that's a big M right there. So the mass of the planet increases. That makes the fraction bigger, which makes the velocity of what bigger?
Of the planet bigger.
The velocity of
Satellite.
the satellite. Remember what this V is talking about. It's talking about the satellite. Okay, good. So this is an important equation for us here. So that formula was specifically for a circular orbit. And if the speed differs at all, so if somehow the speed changes, then the orbit becomes more elliptical rather than circular. And so when we did that simulation with the orbits, if you changed anything, what happened to the orbit?
It changed.
The orbit didn't just suddenly become a bigger orbit and it was circular. It became more elliptical, okay?
Or the planets just freaking crashed.
Well, if they didn't crash into each other, yeah.
Sling off into space.
Right.
That made me mad.
Okay, so yes, the orbital speed does not depend on, which M is this?
The small m. So
The orbital speed does not depend on the small mass, the mass of the satellite, because it's in free fall, and we know that free fall does not require us to know the mass of the object. All objects fall at the same rate. So the motion does not depend on the falling object's mass. For a planet orbiting a star, the period t, remember we use capital T for period, is the time to complete one full orbit. We know that v equals 2 pi r over t from previous sections. So if we combine that with the previous equation that we just saw, we have 2 pi r over t equals the square root of gm over r. So now we have another equation that we can work with. So if we rearrange all of that, we have a new formula that expresses the relationship between the period of the satellite and the radius of the circular orbit. This guy, t squared equals 4 pi squared over gm times r cubed. And notice the way that I wrote that. We have this 4 pi squared over gm here. This is all constants. 4 pi g and the mass of the planet, those are all considered constant. They don't change. The period can change, the radius can change. Those are your variables here, okay? So the square of the period, t squared, the square of the period of the orbit is proportional to the cube of the radius of the orbit. Proportional to the cube of the radius of the orbit, okay? So if I change the radius of the orbit, the period will be proportional to that radius cubed. the period will be changed by the square. Okay? So this formula is very straightforward. In this section, we're going to be solving problems involving that formula. So communication satellites appear to hover over one point on the Earth's equator. There's a word for that. The satellite appears to remain stationary as the Earth rotates, is said to be in a geostationary orbit. What is the radius of the orbit of such a satellite? So we have all kinds of satellites that are up there. They're all over the place. If you look out in the night sky, especially for us around here, our night sky is so dark that you can see hundreds of satellites if you go out and look all the time on a clear night. Just go out and take a look up, and you'll see spots of look like stars, and they're moving all over the place in every direction.
Or like that line that just goes across the sky. Right?
Or yeah, I guess you can see Skynet flying across the sky. Yeah, it is. It's like Skynet.
Really?
Yeah, no, it's
Dude,
not Skynet.
It's kind of crazy.
But yeah, you can
Am
see
I the
those.
only one who got that?
Just go out and look. You'll see satellites streaking across the sky all the time. But you won't see a geostationary satellite moving because it's sitting up there. It's parked basically relative to us. It looks like it's not moving, but it is. It's in orbit just like every other satellite. But relative to us, it is not moving because it is orbiting at the same rate that the Earth is turning. Okay? So the question is, how far up there does it have to be in order to be in an orbit that is moving at the same rate that the Earth is turning?
So then we need to know the mass of the Earth for sure in this.
We know what the mass is.
So what we're going to do is we're going to use that formula. Okay? So the period of Earth,
Square.
what is the period of Earth?
The time it takes to
The time it takes for Earth to do what?
revolve once.
Revolve once. And what is it?
24 hours.
24 hours. So in other words, this satellite has to go around once every what?
24 hours.
Same thing,
Wait.
right?
How did you figure that out?
Because it's got to return to the same spot just like we do, okay? Okay, it was a joke. All right, fine. So we have the same formula, t squared equals all of these constants, 4 pi squared over gm, the mass of the Earth, r cubed. Okay, so the question is, what is the radius of the orbit?
So we
Well,
need to
we
solve
divide
that
by-
for-
We got to
Divide
solve
by
for r
everything.
cubed, okay, which means we got to solve for r. So the first thing we're going to do is, you're right, we're going to divide by all of these constants. So when I divide, really what I'm going to do is I'm going to multiply by the reciprocal. So when I multiply by the reciprocal, that gives me gm
T-squared.
over 4 pi squared times t squared. So that t squared is going to be in the numerator. Now I want r cubed to be just r. So how do I do that? Cube root the whole thing. And that gives me r. Okay,
how
so
come T went on top?
we had the reciprocal. We multiplied both sides by the reciprocal of all these constants. So gm over 4 pi squared was multiplied by t squared. So I just put it in the top. Okay? All right, so now we can plug in all these numbers. So we have the cube root of g is what?
6.67 times 10 to the negative 11.
6.67 times 10
Negative 11.
negative 11. Units are
Newtons, meters per seconds.
meters squared per kilogram squared. Okay, now mass is which mass?
The mass of the Earth.
Mass of the Earth is what?
Is 5.98 times 10 to the 24th.
5.98 times 10 to the 24th. What?
Kilograms.
Kilograms. Okay, and now period squared. We said period is 24 hours. Can we use 24?
No, we gotta change it to
Seconds.
We got to change that to seconds.
And then
Okay.
we have to
So
put
3,600 times 24.
There's 3,600 seconds in 1 hour, so times 24 gives us how many?
86,000.
86,400 seconds. So we'll put that here, 86,400 seconds. And this is squared. Okay. And all divided by 4 pi squared. All right, we plug all that stuff in. What do we get? So 4.2. How many significant figures do we have here?
We were not given anything.
We weren't even given anything, were we?
No.
Okay, so the best we have is
3.
this is a constant. That's 3. I guess we could say 4.22. 4.22.
Times 10 to the 7.
10 to the 7th. Okay, so what's the units then?
Meters.
Is it meters? Okay, meters. All right, so what is this? So we understand it.
That's the radius. That's how far the satellite is from.
Okay.
From the center of the Earth.
It's the radius from the center of the Earth. That would be 422. If I move the decimal 7 places, right? It was after the 4. So 1, 2, 3, 4, 5, 6, 7, commas. Okay, 42 million
200,000.
meters. But if we make that kilometers so we actually can understand this, these guys would go away. So basically, this is like 42,000 kilometers from the center of the Earth.
How far is the center of the Earth?
Okay, so what's the radius of the Earth then? That's a good question.
That's probably in this.
The radius of the Earth is 6.37 times 10 to the 6th.
6.37
In meters or kilometers?
times 10 to the 6th meters.
So actually, the third. If we switch it to kilometers to make it easier.
Okay, so this would be 637. So that's 1, 2, 3, 4, 5, 6 meters. Get rid of those 3, and now we have kilometers.
And we can subtract that to see how far above the Earth it is.
35,000.
Right. So yeah, it's going to be around 42,000 minus 6370, whatever that winds up being, above the surface of the Earth. That's pretty far, right?
Yeah.
In order for it to be geostationary. So we have satellites way out there orbiting the Earth just so that they can always look at the same spot on the planet. And so they're always above the United States, beaming down whatever it is they're beaming down, this whatever communication they're trying to do, whether it's radio, so like Sirius XM satellites always beaming down. You wonder how you can always hear the radio station no matter where you're at. That's how. They're up there 42,000 kilometers from the center of the Earth, beaming down, Hairy Nation or whatever it is, okay? So that's it. That's how they're able to do that, okay?
So then what's the point of the ones that just sit there and go around you?
So now the communication satellites, that would be like, what is it's not Skynet. What is it?
It's the SpaceX stuff that he put.
Yeah, that one. That's in a low Earth orbit. So that internet network has put up thousands of these things, or in the end, it's going to be thousands of these strings of satellites in a low Earth orbit. And the idea there is they're putting up so many of them that no matter what time of day, no matter where you are on the planet is the key. You're going to always have a network to log into. So those are buzzing around the Earth at a low orbit, so that no matter what, you're always going to have a line of sight on one of those tiny satellites. Okay.
Even if you're up in the mountains and there's no cell towers.
Even if you're up in the mountains, you will always have a satellite overhead so that you have a signal. It's very expensive and difficult to put a satellite up in a geostationary orbit. It's cheaper and easier to put these strings of satellites up in a low Earth orbit. But it's a pain in the butt for anybody who's trying to look at the night sky and enjoy it when you have a string of 152 dots going overhead cluttering up the stars, because now, without a doubt, you're going to see all of these lights going overhead, ruining the night sky. So there's a trade-off. So anyway, one man's thought, I guess. So this one, each year the radius of the moon's orbit increases, this is true, by about 3.8 centimeters. So 2.54 centimeters in an inch. That's obviously more than an inch. If I doubled 2.54, I'd have about 5. So it's between 1 and 2 inches per year. How does this change affect the length of a month? A month gets longer, a month gets shorter, the length of a month stays the same. What do you think? The radius of the moon's orbit increases by 3.8 centimeters. Does this mean the month gets longer, the month gets shorter, or the length of a month stays the same?
The month is going to stay the same.
What is a month?
Well, based on the Gregorian calendar, it's
Was it January, February?
it's about as long as the moon takes to go around, or to change all of its phases.
The length of a month, the word month comes from moon, and it is the amount of time it takes the moon to go around Earth one time.
But
if we're talking about the calendar month doesn't care about how long it takes the moon to go around the planet one time.
Well, we know it goes around 28. It takes
But
28 days.
What this question is really asking is, how will this affect the period of the moon?
Phases. Yeah.
And so, if the radius of the moon's orbit is increasing, how will this affect the period of the moon?
I think that equation should come in handy. Right
That equation definitely will come in handy. The equation is t squared equals all those constants r cubed.
And so if the radius is increased, then the period is increased.
If r got bigger, then t must get bigger.
You could guess that means A.
That means
I
A.
said B because I was thinking of the wrong formula.
And actually, this is kind of an interesting thought, so I'm going to say it, and I'm going to say it while this is recording. The moon is getting farther and farther away. And based on the problem that we just did, geostationary orbit for a satellite, there is a point at which a satellite can get far enough away that it is in a fixed spot relative to us, right? Which means if the moon is a satellite and the moon is getting farther and farther away, eventually there is a place in the moon's orbit where the moon will be far enough away that it will not move in the Earth's sky. It will be stationary relative to us.
Yeah, but then in time it's going to go farther out. Or it's going to
No,
hit that point stop.
It will become stationary in our sky eventually. That won't happen in our lifetime. It's going to take thousands, if not millions of years, but it will eventually become stationary. It is already tidally locked to us. By that I mean we don't see the backside of the moon. Not the dark side, but the backside. We see the dark side all the time. We don't see the backside of the moon because one face is always facing Earth. The other side does not ever show its side to us. That's tidally locked. It can also become stationary in our sky, and eventually it will because it is getting farther and farther away. Okay? There are other satellites in our solar system that are stationary relative to the planet, and eventually ours will become stationary. And when that happens, it's going to be interesting because tides, circulation of airs and waters and things like that on our planet depend on the moon changing its position relative to us. And when that stops, it's going to be interesting. So anyway, kind of an interesting fact.